All right, so this is, like I said, this is probably the second hardest day of the year, and we cover really a couple weeks of chemistry today. So all we're gonna care about right now is electron orbitals. We don't care about protons, neutrons, arrows, any of that, isotopes. We just care about electrons right now. We're going to start with orbitals, but by the end of the day, we're going to get rid of orbitals, all right? And make things a little bit easier, and we're going to do Lewis dot diagrams. Some of you guys know what those are. We're going to do dot diagrams by the end of the day. I've left these definitions from the last class on the board because I want to make sure they're consistent throughout the day. I'll fix that in a minute. So I'll kind of define those as we go. Just leave them for now. All right, so we want to start by doing the orbitals of fluorine and sodium. So go ahead and put those on your paper. I'll give you a minute to catch up. And when you get finished drawing the orbitals, go ahead and circle the valence electrons. It's like opening your candy wrapper in church. You open it a little bit, preacher looks at you. Let's do it. All right, so sodium has how many valence electrons? One, and fluorine has 7. Now, we went over the octet rule yesterday. The octet rule says that to be stable, they want to have 8. Now, I want to be clear here. I will use teleological expressions, and I don't mean them. And what I mean by that is this. If I ask, why does your heart beat? Some of you might answer, well, because it needs to get blood through the body. It wants to get blood. It doesn't care. Your heart does not care about your blood through the body. It reacts because of a chemical reaction that's going on in the cells. It's an active calcium channel pump, right? It doesn't care about your blood or your body or anything else. It's reacting to a chemical reaction, all right? Now, same is true here. Sodium doesn't want 8 valence electrons, all right? It's a reaction that occurs. So don't think that the fluoride's over here going, oh, I just need one more electron. It doesn't care. It's reacting, all right? So when I say it wants, it doesn't really want. You know what I'm saying, all right? So the fluorine needs how many more electrons? 1. All right? And sodium it needs 7 more. What if we were to axe this guy? Does it have 0 if we get rid of that one? It has 8. I hear light bulbs. I hear them. Right, so if I can get rid of this 1 electron, we get rid of the level 3 altogether, and we're down to 2, and I have 2s and 2p with 8. Right? You guys see that?
Yes.
So what we're going to do is donate this electron there. Sodium's like, hey, fluorine, do you want me an electron? Yeah. Fluorine's like, yeah, I'll take your electron. Thank you. Let's be friends. All right? So now I have sodium bonded to fluorine. sodium is now bonded to fluorine. It has given an electron to fluorine. That is an ionic bond. An ionic bond is a bond where one atom donates an electron to another. Then I'm going to write a little parentheses here. I said it to the last class, but I didn't write it. It's always a metal and non-metal. So we're doing this definition right here. Ionic bond, bond where one atom donates an electron to another. Always a metal and non-metal. Yep.
So do we write it like that?
I'm gonna
Dash
get.
in between them?
That's the bond. It's not a dash. It's a bond. I'm gonna show you how to write it. That's the next thing we do. So when we write the name of the ionic bond, naming right here, naming, write the metal first, and the non-metal with "ide" at the end. So this would be sodium fluoride. Sodium fluoride. And we would write that compound NaF. NaF. And that would be the chemical formula, NaF.
Don't they use like some kind of fluoride that like this?
Yes. Now, I'm going to do one more example like that over here, and then we're going to really simplify and start learning how to do some cool stuff with it. So, let's do magnesium and oxygen over here. Magnesium and oxygen. Anybody have Emma Horn's phone number?
I do.
Can one of you guys text her and tell her I forgot to have her do her makeup test today?
Yeah.
Just tell her she can do it during school or she can come and do it Monday. Thank you. She asked to do it and then I forgot. And she was probably frightened to remind me or something. All right, how many valence electrons on this magnesium?
2.
2 valence electrons. And how many on this oxygen? 6 right here. 6 valence electrons. Now, we can do simple math. If you understood this example, then this should be easy, right? What can I do here?
Take the 2.
Right? Give these 2 electrons here. And so now I have what compound? Magnesium oxide. Magnesium oxide. All right, on your periodic table, cover up transition metals. Those are confusing. We'll come back to this. All right, we have 1, 2, 3, 4, 5, 6, 7, 8, right? That's what we talked about yesterday with valence electrons. All right. Noble gases have how many valence electrons? They're gonna bond to nothing really. Now, the halogens have 7. And the alkalis have
1.
1. So does it make sense that they would bond together easily?
Yes.
1 and 7. And then this column, the alkaline earths, and then the oxides here, the 6th one. Does it make sense that they would all bond together easily? 6 and 2, right? And you go in one more to here. 3 and 5, right? Does that make sense? Okay. Now the carbides, the carbon group, we'll come back to. They're a little weird because they're at 4, right? Give or take. It's kind of weird. All right. So we'll come back to that. Now remember, it does have to be a metal and a non-metal. So boron's a little weird as well. All right. So, but it should make sense to you that 1 and 7, 2 and 6, 3 and 5, right? Should be easy. When one atom ionically bonds to another atom, that makes a binary compound, right here. A binary compound is a compound between only 2 atoms. A binary compound, bi means 2, right? Binary compound, compound between only 2 atoms. So this would be a binary ionic compound, and this would be a binary ionic compound. Does that make sense? Sorry. Both of those would be binary ionic compounds. Ionic compounds, metal donating to non-metal between 2 atoms. Binary ionic compounds. Now I want to show you a Lewis dot diagram real quick. The Lewis dot diagram, right here, is the way to model of valence electrons of an atom by drawing them around the chemical symbol. So model of valence electrons of an atom drawn around the chemical symbol. Now, I do them a certain way. Ms. Fisher and I had this conversation this week. I think Tuesday of this week. It might have been last week. We had a conversation about how we draw them, because we do them differently. And so I went and looked up, and people do them 2 different ways. So I'm going to show you how I do them. She does them slightly differently, and that's fine. All right? But I do top, bottom, right, left, repeat. Top, bottom, right, left, repeat. So we draw the valence electrons around the chemical symbol. So, for instance, if I was doing fluorine, I write the chemical symbol, which is just F. How many valence electrons are on fluorine?
7.
7. So I do top, bottom, right, left, top, bottom, right. 7 valence electrons. Top, bottom, right, left, top, bottom, right. Fluorine. How about for sodium? Sodium has how many? 1. Put a dot above it. How much easier is that than drawing orbitals? Huh? What about oxygen?
7.
Right? So top, bottom, right, left, top, bottom. And for magnesium, top, bottom. So now we've done Lewis dot diagrams for all of these.
Can we just start doing those?
Yep.
Good.
Unless I ask you to do the other. Which on the test I'll ask you to do both. So you need to know how to do both.
I don't understand. Can you explain how, like, to get the valence electrons, like, how do you know which ones are and which ones aren't?
Remember, it's the highest numbered energy level.
Yeah.
All of that number. So 3s, just 1. Out here we have 2p, 2p, and 2s. All of that highest number together.
Oh. Okay.
Got it? Or you can just look at the periodic table and you know how to do that way, right? Okay. So let's look at one more here. potassium. I'm going to throw potassium in the mix. How many valence electrons does potassium have?
1.
1. It's so much easier, isn't it? No 19 electrons. All right? And what if I have potassium and oxygen? The two examples we've looked at before have been binary. I have sodium with fluorine, I have magnesium with oxygen. That's easy. But what if I have potassium and oxygen? What happens? Jake, what happens if I donate that electron from potassium to oxygen?
We only have 7.
Right. Potassium's good. But I only have 7. Anybody have a suggestion?
With another potassium.
Another potassium. Right? If I have another potassium, right? Is everything happy now? Is everything stable? Yes. All right? This would be K2O. K2O. I have 2 potassiums and 1 oxygen. That's an ionic compound. It's not a binary anymore. We have 3 atoms. But it's an ionic compound. K2O. What would we name that?
Di.
Nope. No, we don't use any numbers in ionic bonds, just in covalent. We're not there yet. So we just call this what? No, we're not there yet.
Potassium.
That's going to make it a lot of fun in a day or two. Potassium oxide. That's it. That's all we need. Ionic bonds, the numbers are assumed because it can only be one way. It's potassium oxide. When you see things, we're going to do covalent bonding next week, but when you see things like trioxide or things like that, dioxide, whatever, when you see a number before the name, that's a covalent bond. Potassium oxide. I have potassium and oxygen. Potassium oxide. Now, let's look at some charges. We call them oxidation numbers. That's written here. And sorry, it's kind of covered up by my daughter's artwork. Oxidation numbers. Oxidation number is positive or negative number. Oxidation number is the positive or negative number that shows the number of electrons lost, gained, or shared by each atom. Oxidation number is a positive or negative number that shows the number of electrons lost, gained, or shared by each atom. Now let's start with sodium and fluorine. Sodium fluoride here. What happened to sodium in this bond? It lost an electron. Now this is where it gets a little bit confusing. Just gotta be careful. If I lose a negative, electrons are negative, right? If I lose a negative, I become positive. So this is Na plus. F would be, fluorine is gaining an electron, so it is minus. Na plus F minus. Now look at magnesium oxide, MgO over here. Magnesium did what? Lost 2 electrons, so losing minus a negative makes it 2 positive. 2 plus. And oxygen gained 2 negatives, that makes it 2 minus. Isn't this so much fun? It's like math and science. It's like two wonderful worlds meeting. All right, now it's time to get a little trickier. Let's look at this one. Let's look at this one. Oxygen's easy, right? What's happening to oxygen? Gaining 2, so it's going to be 2 minus, gaining 2 negatives. Now, look at that definition. Number, oxidation number, I can't read it from here. Positive or negative number that shows the number of electrons lost, gained, or shared by each atom. By each atom. We have 2 potassium atoms. What is happening to each of them? Losing 1 electron. That makes it plus. Each one of those 2 is losing 1 electron. Now, let's do some quick multiplication here. I have 1 sodium losing an electron. I have 1 fluorine gaining an electron. So I have 1 plus and 1 minus. That equals 0, right? I have 2 pluses and 2 minuses on 1 atom each. That equals 0. I have 2 atoms each losing electrons. So that's 2 plus. I have 1 atom gaining 2 electrons. That is 0. Always equals 0. Right? These charges, these oxidation numbers times the number of atoms with the positive and negatives will always equal 0. All right? Questions so far? Yes.
What about like the polyatomic ions?
We'll get there. I'm not there yet. Now, look at your periodic tables. Your fancy, awesome periodic tables.
Yeah, there you go.
Isn't it beautiful?
Pardon me, can you send Charles Coggins to the main office?
Yes.
Thank you.
Look at your periodic tables. Look at fluorine. What's it called on your periodic table? Fluoride. And what's it got next to it?
Minus. Dang, this stuff good.
I'm glad I got that on recording. All right. Look at sodium. What does it have? Plus. All right. Look at oxygen. What does it have?
2 minus.
2 minus. Does that all make sense? All right. Now we haven't gotten to. Emily just asked about the polyatomic ions. It's up at the top of the page. Now we're not doing those today. We're going to get to them. But look at those charges. Can you guess what they would bond with?
Yeah.
Right. If I look at acetate, what's it have at the end of it? Minus. So we'll bond with anything that needs to give one, right? Does that make sense? So we'll get to those next week. Now, here's what we're going to do. I'm going to put a list of atoms on the board. About to see what you guys can really do here. All right, let's do RB, NE, CL, N, AL, and I had one more last class. What was the other one? CA.
Do the dots?
The dot diagrams for those 6. How much easier is that, right? Draw the Lewis dot diagrams for those 6. Top, bottom, right, left. Top, bottom, right, left. Dot diagrams for each of those. Now, remember we can just look at the periodic table and tell how many valence electrons it would have. Charles is writing the dot diagrams for these 6 atoms. Oh, okay.
Pardon me, is Charles on his way to the main office?
Yeah, he's
Thank
giving
you.
everybody hugs real quick. All right. Rubidium. Making a bold dot. I can't see that. Nitrogen.
Really?
Neon. Original. Aluminum. That's bad throw. Good catch. And calcium. Calcium.
I don't think I'm told nitrogen.
Step stool. Make sure the dots are bold enough everybody can see them in the back. It's a super electron.
So we make gold dot, it made gold dot. I kind of made
Hey, you already did nitrogen.
I did.
Do neon.
I know there's someone figuring out a table. I don't have it back there.
It's a noble gas, bro. What? It's a noble gas.
Okay. What does that mean?
They're stable because they have.
He's always got that like
I'm telling you this. I don't like this section.
I need to be able to see them, man.
You can't see those?
No. All right. So we have rubidium has 1 valence electron, 1 really big valence electron. Chlorine has 7, top, bottom, right, left, top, bottom, right. Nitrogen has 5, top, bottom, right, left, top. Neon has 8, so all 4 sides are full. Aluminum has 3. Calcium has 2.
I got them all wrong.
Well, good news is the worst you'll have to erase is 48 dots.
What?
I love
All right,
I'd like to know how.
everybody, listen. Anybody that's lost, lean over to the person next to you and ask them to help you real quick. All this should make you want to celebrate the life of Demetri Mendeleev. Dave Harry. All right. All right, here we go. So if I asked you, make binary ionic compound.
Interruption, but Ms. Gore's field trip for community is, the bus is out front at this time. It should be a small group, but
It's time to go.
Binary ionic compounds. Binary means how many atoms? 2. And ionic means metal donating electron to non-metal. All right? So, is there anything up here that just needs 1 electron from rubidium? What? Chlorine. Rubidium can give 1 electron to chlorine. That's going to be RbCl. What is going to be the charge on rubidium? Positive. It's giving away 1 electron. And chlorine is going to be negative. And we're going to call that what? Rubidium chloride. Is there anything else with 7 that rubidium can just bond 1 to 1 with? No. So we're done with the rubidium. There's no other binary ionic compounds rubidium can do. Alright, and that's a non-metal, non-metal, non-metal. Let's go back to the next metal, aluminum. Is there anything that aluminum can give all 3 of its electrons to?
Nitrogen.
Nitrogen. Why? Because nitrogen has 5. So I can do aluminum with nitrogen. Al. In. What's going to be the charge on aluminum? It's giving away, 3 plus, and nitrogen is going to be 3 minus.
When we write the compounds, do we have to put the oxidation numbers?
If you're asked for them. Like on a test, it'll say write the compound with the oxidation numbers. And what's that name going to be? Aluminum nitride. The last element up there is calcium. Has 2 valence electrons. Is there anything that needs just 2? No. Something would have to have 6, right? So those are the only 2 binary ionic compounds we can make. What about other ionic compounds? Now there are some tricky ones we're not going to get into, but some basic ones we can look at. Rubidium, let's just always start with metals, makes it easier. First of all, what can we just delete off our list? Neon. Why? It's 8. It's stable. It's a noble gas. Right? It's child's play. It's inert. It's a noble gas, man. So it's like so last week. So neon we're not worried about. Let's start with our metals. Rubidium we already did with chlorine. Can I do rubidium and nitrogen?
Yeah.
What would happen if I gave 1? Rubidium is